Good afternoon. This is Schweitzer, and we're running in a series of videos here looking at some information on graphing motion. So, in this chapter, even though there's lots of ways you can graph motion, these are our three most common ways. We have our position time graph, velocity time graph, and maybe not as common, acceleration and time graph. So position time graph, of course, here, the slope is the meters per second, let's just say hypothetically, and I'm sorry, let's back that up here, meters, seconds, and therefore the slope is meters per second, which is velocity. Okay, and then here we have a slope here, which is going to be meters per second squared, and then the area of the curve is meters. That's important. This area doesn't always do much for us. And then we have acceleration. Okay, so this is a new graph for us here. So just tracks acceleration. We could have an acceleration that is like this, which is constant. Okay, that would be a constant acceleration, which is pretty common when we're doing stuff in physics. You could have something that like this, okay, which means that we're increasing acceleration at a constant rate. Um, and of course, right here, the zero would be no acceleration. We could have it is a vector, so we could have a a positive acceleration. Acceleration. Let's do that here, and let's do a negative acceleration at the bottom. Okay. Area of the curve for this guy technically would be meters per second squared times seconds equals meters per second. Okay, so for not as useful for us for area of the curve, it is considered velocity. So we could get something out of that. Okay, and then the slope for this guy here. So this is the area. And then this slope is going to be meters per second squared times 1 over seconds is meters per second cubed. And this actually has a name which is called jerk. And you should hopefully be looking at this in it's an R there. And in this sense, it's your rate of change, okay, of acceleration. We call it jerk. Not, it's around, but it's not as common. So if this jerk would be zero, this would have a jerk, positive jerk. This would have a negative jerk, and so on and so forth. Okay. So a couple of things about our three main guys here. Really got to be familiar with these two. This is like 98% of the problems are on these two graphs. This one pops up rarely. Okay. Again, what do we got here? What do the units mean? Kind of summarize this already. Let's do it again here. Okay. What do the units mean? Well, we have the meters per second squared, so acceleration here, and we got time here, which could be in seconds. All right. We have your jerk, which is meters per second cubed, and we have meters per second for the area and the curve. What would a flat line be considered? Okay. The flat line just simply means that my acceleration is not changing. Constant acceleration. How do we speed up? Well, anytime you have any acceleration, um, you have a change in velocity. So speed up. Typically, we have a positive velocity with a positive acceleration, or we would need to have a negative velocity with a negative acceleration. So for this graph, we can easily tell if we about this aspect of the information. So let's say, for example, like in gravity, for example, um, gravity is a constant acceleration. Okay, never going to change. So what would gravity's acceleration be? All right. Well, it's just negative 9.8. So it would, first of all, it's going down always. So let's say this is negative 10 or negative 9.8, and that's meters per second squared. So I'm actually going to use a straight line here for this because it's straight. And it would just come across like so. Okay. This would be gravity. So can we tell if we're speeding up or slowing down here? Really, if I throw a ball up, okay, and comes back down, the acceleration never changes. So here I have a positive velocity, negative acceleration, negative velocity, negative acceleration. So here I'm speeding up, here I'm slowing down. So I really can't tell if I'm speeding up or slowing down from this graph. I just can tell half of it. Okay. All right. So again, we just talked about throwing a ball up. So let's detail that a little bit better here. I take a ball, okay, and if we're in class, we likely just do this. And you take a ball and you toss it up, and it comes up to some point and comes back down in the same spot, and you catch it in your hand. Okay, so essentially the ball goes up, okay, and let's say it reaches a peak right here, peak right here, peak right here, hits back your hand right here, okay, so we can match all these guys up. And of course, we always want to try this stuff on our own before we really have me look at it for you, but it's going up, and it's in only traveling in the vertical position. It's not going left or right. So we're only tracking really the movement in the y coordinate. Okay, so either way, so the slope is the velocity. You should note that it's slowing as as you go up. We have a as this ball goes up, we have a negative um, acceleration, but a positive velocity. And then as it comes down, we have a negative acceleration and a negative velocity. So we're speeding up on the way down. We're slowing as we go up. So I wouldn't want to use a straight line. Like something like this would not be accurate because this is showing a constant slope, and that's showing that the velocity is not changing. The velocity holds, stops, and comes back down. So we don't want to do that per se. So we probably want something that looks more like this. All right, and like that. Okay, and my line could be moved over here a little bit. Okay. All right, so now velocity. Okay, now again, this slope is representing now in the line. Okay, so but I would the line represents this slope. Okay, so what's this going to look like? Now, in this case, the slope on this line is acceleration. So the acceleration in this scenario is negative 10 meters per second squared, or constant. Okay, so what would that look like? Also note that at the beginning time, it's driven the fastest as possible. It's got at the beginning here, we have the maximum positive velocity when I leaves my hand. Maximum positive velocity. And then when it hits the ground coming down, I'm at maximum negative velocity. So the beginning at maximum positive velocity, here you have maximum negative velocity. So and the slope is negative 9.8, which means that this is a negative slope. So I'm going to say this might be my maximum top speed, and therefore right here, okay? And the line is just going to be straight through here, and there we go. Constant slope, meaning we have a -10 or -9.8. Maximum velocity at the peak, which isn't perfect. It'd be nice to hit that line right there. We have 0 velocity. That's right when it reaches the top. And then it changes direction and comes back down. Okay, and then acceleration. Okay, it's just going to be right like that. Okay. All right, that's not easy. Okay. So the next question says, on this next thing, I'm going to bounce back here, is how would the ball's thrown directly up in the air and allowed to drop to the floor? How would your graphs change? Okay, so I'm just gonna maybe grab a different color pen, and what happens here? Each one. Okay, so this guy just continues to hit the ground, let's say right here, and we would get more and more velocity, so our slope would be getting like that, steeper. And then the velocity here, this guy would just continue to gain more velocity, and this one would really be unchanged. Okay, and then it hits the ground. Okay, hitting the ground would cause this thing to shoot very quickly to 0. Okay, all right, that's that guy. Hold on. Okay, acceleration. So just again, as we're doing some of these things, you should be aware that math is right around the corner, and we don't want to completely ignore some of the basic formulas. So acceleration is really the change in velocity. So it's going to be velocity final minus velocity initial, and then we're going to divide that by your change in time. All right. So let's derive a formula for velocity final. So first thing I would do is probably multiply over acceleration times time equals Vf minus Vi. So this is part of a derivation process. We have a beginning, a middle, and an end. And then I'm going to just take and add over my Vi. So it's going to be Vi plus a t equals Vf. And this is a super common formula for us mathematically. Again, acceleration equals Vf minus Vi over t. Just get rid of that. Okay, divided by your time. Sometimes I do substitute Vf. Okay, I use a different variable here, which is just Vt, which means the velocity at a certain time. And the time is right there. It's the velocity at that time. I kind of like that better. Velocity initial, velocity time at this time. All right. I believe that brings us to the end here. Thank you very much.